Hi everyone, and welcome to another AP Calculus video. We're going to continue our discussion of integrals, and today we're going to discuss something called the fundamental theorem of calculus. And so let's consider we have some random integral, and we've got some function f of t, and we want to integrate f of t from a to x squared. Well, the graph of this might kind of look like this. If these are my axes, and this is my function. So a is any arbitrary spot on the graph, and then x squared is just going to be some other arbitrary spot that depends on x. Now notice I've got different variables going on in here. I've got t, so x is just some other extra variable. It's an arbitrary variable, so this is t on the x-axis. Don't get it confused. And then this would be y or f of t. So we have to understand that we have a different variable happening here, and x is a completely different function. So we have a function f of t, and then we have x, which x squared, we could call that some other function, g of x. So let's keep that in mind. We're going to have to deal with compositions of functions here. So let's consider this, and let's take it back to the most basic thing that we've understood. We've already learned that when we evaluate an integral, we use an antiderivative. So I'm going to write this as f of x squared minus f of a. So this is actually part of the fundamental theorem of calculus, and we'll get to it at the end. We've actually been using it to evaluate integrals. So this is how we would evaluate this integral. We'd use antiderivatives. Now, suppose we want to take this function, and I'm going to erase this to give myself just a little bit of space. Suppose we want to take this function, and now we want to find the derivative of it. So I want to find the derivative. So essentially, I'm doing the derivative d dx. Now notice it's with respect to x, not t. That's important. We have an x here and a t here. So lots of variables floating around. So we're doing d dx of this f of x squared minus f of a. Now let's be clear. Let's understand what's happening here. Capital F of a, this turns into a number. This turns into some function of x. And I don't like to use f because it's confusing. So some function, some equation with an x in it, right? So when we do this derivative, capital F of a is a number. So this is essentially, we're going to do the derivative d dx of f of x squared minus d dx of f of a. Well, this is going to go away because the derivative of a number, of a constant, is going to be 0. So it doesn't matter what a is. A could be any number. It's always going to go away. So now I'm left with this. I'm going to do d dx. I'm going to do the derivative of f of x squared. Well, remember, capital F is the antiderivative of lowercase f. So if I'm going to do the derivative, f prime is just f. So that's a notation thing that we have to understand. So again, if I go off to the side here and just kind of remind you of some of our notation, if we have f of x, as we derivative, we get f prime. As we derivative, we get f double prime, which means as we derivative this, we get lowercase f. Now, as we integrate, this is what we're getting. So as we integrate f double prime, the result is f single prime. As we integrate f prime, the result is f. As we integrate f, the result is the antiderivative capital F. So it's this whole continuum of notation that we have to deal with. So when I take the derivative of capital F, this is going to be essentially f of x squared. But it doesn't stop there, because we have to remember that when we have x squared being a function, remember x squared is g of x. So f of x squared is the same as f of g of x. And we know that when we do the derivative and I guess I should be doing this, capital F of x squared is capital F. So when I do the derivative, f prime of x squared it's going to be f prime of g of x times g prime of x. So it's going to be f of g of x, because f prime is lowercase f, times g prime. So here, it's going to be f of x squared times 2x. So I'm essentially using the chain rule, and I always forget, I apologize, I keep writing behind my face. We have to use the chain rule here as we're doing this. So when I go back down here and I write in that 2x, this is where it's coming from. It's that chain rule that I have to apply. So chain rule says multiply by a 2x. So this becomes the derivative. So anytime that I am differentiating something like this, where I want to find the derivative of an integral that goes from a constant, any constant, to some function of x, and I have t's floating around, when I do the derivative here, essentially what I end with, and we just saw this, was we ended with f of x squared. Notice I just put in the x squared, but then I had to multiply by 2x because it's the chain rule. It's the derivative of that function of x. So this was my end result. And so what does this kind of teach us? It teaches us that when I have a derivative and an integral, they cancel each other out. They kill each other. And they are no more. We just have to remember that we put in that x squared for t, but then we have to tack on the chain rule because we're doing a derivative, and anytime we're doing a derivative of some function inside of a function, we have to tack on its derivative. So let's kind of see how this works. Let's put it into play. Sometimes when we do the introduction and we try to explain the concept, it can be a little bit muddy, but once we start doing a few examples, I think it'll come together. So if f is a continuous function, then this function, capital F of x, equals a to x, is essentially, this is what's happening. We have an antiderivative, right? So we have a derivative at every point x in a, b, so that when we take the derivative and the integral kill each other, and we're left with f of x. The only tricky part is this, and here's what I was getting at with my introduction. Suppose that instead of having some function of x, or instead of having just an x there, and this is really what we should be writing down. If u is some function of x, okay, we've done this before with our chain rule, then when we do this derivative, the derivative and the integral kill each other. We put u in, so that's what's happening here. We'll get a highlighter. That's what's happening here. But then whatever u is, we have to multiply by its derivative, du dx. So in the same way that we have du dx on all of our derivatives from Unit 3, we have to use it here as well. So let's do some examples. So here, u is x, which means du dx is 1. Anytime du dx is 1, we don't need to worry about it. But we always need to think about it in the back of our mind. So if I want to find dy dx, that means that I'm going to find d dx of this integral. And I'm going to notice, okay, I've got x, I'm doing d dx, but in my integral, I have t's. 2 different letters. That's kind of like, that's really important. Because if you don't have 2 different letters, then all this kind of, you have to treat it differently. It may not be what's happening here. We'll leave it at that. But essentially, here's what I'm going to do. du dx is 1, so I don't have to worry about anything. So here's what I'm going to do. I'm going to take this whole function, and I'm going to rewrite my whole function. Sometimes my keyboard feels neglected and wants to be involved. I'm going to rewrite my whole entire function, but instead of the letter t, I'm going to write it with the letter x. That's all I'm going to do. So again, this was my whole entire function here. And we'll use purple. I like purple. And all I did was write it. The integral and the derivative kill each other. They cancel away. X goes in, rewrite it with the letter x instead of a letter t. Ta-da, done. The most basic type of problem. So now let's try this one. Same idea, we're finding the derivative. And again, it doesn't matter what my, what my constant is. The constant's just, it goes away. So if we think back to what we just did up here in the very, very beginning, remember, this constant goes away. So when we do the derivative of a constant, it disappears. So we just kind of skip it and jump straight to the end result. This is what we're doing. We're skipping all that explanation and just jumping to the end result. And this is the fundamental theorem of calculus. So here, u is 3x squared. Du dx is 6x. So now I'm going to have to include a du dx. So all I'm going to do here when I do this derivative, d dx, I'm going to rewrite cosine of t with this u. I'm going to put the 3x squared in place. So it looks like this. Cosine 3x squared. Then I'm going to tack on a 6x. That's my du dx. Remember, the rule is, if this is u, we do cosine of u times du dx. That's du dx, that's u. Dunskies. Circle it and walk away. Do not think you need to do more than you're doing, okay? The 6x is the chain rule. So let's keep going. Ooh, this one's interesting. This time, the x is on the bottom. We can't have this. Can't have x on the bottom. So we're going to need a property of integrals. So what I'm going to do is I'm going to switch it. I'm going to put x in the top. But here's the problem. When I switch my limits of integration, I've got to put a negative sign in the front. So anytime I flip-flop those, I have to make the integral negative. So this becomes 3t sine of t dt. And now when I go to integrate this, d dx, I am literally going to write 3x sine of x, but then I'm going to put the negative sign in front. Boom, done. So the u was x, du dx was 1. I didn't have to worry about that. That's all it is. I just have to remember to put the negative when I flip the limits of integration. Let's try one more here for this particular part, and then we'll talk a little bit about part 2, which we actually already know. I just need to tell you that you know it. So here we go. Now check this out. Oh man, I've got 2 limits of integration. That won't do because my fundamental theorem of calculus part 1 says I need one of them to be just a number. So here's where I'm going to have to split my integral. So what I'm going to do is I'm going to rewrite this as the integral. We're going to go from 2x to 0. And why did I choose 0? Doesn't matter. I chose 0 because it was an easy number to write. You can pick whatever number you want. You want to pick pi? Pick pi. You want to pick like 47? Pick 47. Whatever number you pick, though, for this integral, you've got to use it in the other one. So 2x to 0, and then 0 to x cubed. Now I have another problem. And my other problem is that I need this to move to the top. I'm going to have to do one more adjustment before I can just plop things in. So I'm going to flip this and make it 0. Now I am ready. But I'm also going to notice that 2x here, u is 2x. So for this integral, du dx is 2. Over here on this integral, u is x cubed, so du dx will be 3x squared. So I need to consider that when I am working these out. So let's go ahead. We're just going to go ahead and keep that negative sign there. So I'm going to have negative 1. I'm going to rewrite it with a 2x. 2 plus e to the 2x times 2. So now I can kind of clean that up, right? So my negative 1 times 2, I'm going to write it as negative 2. So here's my du dx, multiplied in there, plus. All right, I'm going to do this one. I'm going to multiply by 3x squared. So I'm going to go ahead and put 3x squared up on top. That's my du dx. And then 2 plus e to the x cubed. Whew. That's all I had to do was rewrite the t's as x cubes, or in this integral, the t as a 2x. So here is the final answer. It looks totally weird. And you could go and do this the long way. You could find the antiderivatives and work it out that way and have a grand old time. But this is so much faster and so much more efficient, just knowing that when you see an x in the limit and then your equation has t's in it or any other variable, and you're finding the derivative, that's the key. You're finding the derivative. Don't forget the chain rule, the du dx, and just rewrite it with the new limit, the new variable. That's all. Let me show you what the fundamental theorem of calculus part 2 is. Essentially, it's what we've been using. And it looks like I have a small typo. Let's go ahead and put that parenthesis in. But it says basically this: if f is continuous at every point on a closed interval a, b, and if capital F is any derivative, then when we integrate, essentially we're subtracting. So this, we know this. No problem. We've seen this before. This is not new information. So basically, when we use this property here, we're using the fundamental theorem of calculus part 2. So now we're just going to start calling it that. We already learned it. We already know how to use it. We're just going to call it. And the directions might look like this. So you might see evaluate using FTC part 2. That's all this means to do. So this is when we, in that prior video, we found the antiderivative. So x to the 4th over 4 plus x. We changed it to box notation, and then we plug in the numbers and evaluate. So we're going to have 3 to the 4th power over 4 plus 3. So that's when we plug in 3 minus negative 1 to the 4th power over 4 plus negative 1. So it's not 0 this time, which is unfortunate. So now we actually have to do some thinking. So 81 over 4 plus 12 over 4 is 83 is 93 over 4 minus whatever this ends up being, 1/4 plus negative 1 would be negative 3/4. Oops. Minus negative 3/4. So plus a plus, 96 over 4. Hope I didn't make any little arithmetic errors there. But essentially, this is the fundamental theorem of calculus part 2. And you've been doing it. It's not new information. It's not, you know, it's certainly not new. It is certainly not, you know, anything we haven't seen yet. We're just now going to call it the fundamental theorem of calculus part 2. So if all of this seems confusing, try some on your own. Check yourself that you're getting the right answer. And if you need help, you should always reach out and ask for help. Remember, mastery is not required in the beginning, but a persistent positive attitude will take you farther than you ever thought you could go. So keep trying, keep working at it. Don't ever be afraid to ask for help. Everyone in their life is going to reach a point when something becomes so difficult that you need help with that. Every single person gets to that point, whether they will admit it or not. It happens. And please, if you need help on any of this, please reach out and know that you can do this. I'm here to help you, and yeah, you've got this.